separated set definition, right? Suppose you can take an example R with respect to usual metric. Suppose you can take A equals to open 0, 1, B equals to, for example, you can take open 2, 3. What is A closure intersection B? Are they separated? Yes. What is A closure? Closed interval 0 to 1, 2, 3. This is an empty set, right? A intersection B closure is nothing but what? This is open 0, intersection with closed 2, 3. This is an empty. So therefore they are separated, right? Suppose we can take another example R with respect to discrete, right? You can take any set. Suppose you can take A equals to 1, B equals to 2, 3, 4 going on. Counting numbers. Are they separated? The answer is because A closure intersection B. What is A closure? A closure is itself A because A is a closed set. A is a closed set. A closure is A itself. Intersection B. You know that these two are disjoint sets, therefore empty. Similarly, A intersection B closure. You know B is a closed set because any set which is in discrete metric space is a closed set. Once it is closed, closure is itself. Therefore, A intersection B is an empty. Therefore, these two are separated sets. Right? Now, can you give me an example which is not separated set? Yeah, I can give an example.
Every infinite set is closed.
No, need not be. Need not be. Suppose you
B
can
is
take
infinite
this.
set, sir? B is infinite set.
You know, suppose you can take this. It's an infinite set. Is it closed in R with respect to usual metric? In usual metric, is it closed? No, right? Because it doesn't contain limit points, right?
No.
Zero is a limit point. Yeah. So suppose you can take yeah. These are my separated sets. So let us go through the simplest properties. First property is separated sets are always disjoints. Right? This is straightforward. You know, separated sets means what? A closure intersection V is an empty and A intersection V closure is an empty. That means A closure, you know that A closure is the smallest closed superset of A. You know that A is contained in A closure. By using this property, this can be rewritten as A intersection B contained in A closure intersection B. You know, right side is empty means what? Subset of empty is always empty. Therefore, it's an empty. Therefore, separated sets are always disjoint sets. What about the converse? Converse may not be true. For example, you can take R with respect to usual metric, right? Suppose you can take A equals to, what do you take actually? Open 0, 1. Yeah, you can take close 1 and open 2. Yeah. Are they disjoint? Yes, they are disjoint. Are they separated? No, separated. Because A intersection B closure is closed interval 0 to 1, intersection with closed interval 1, open 2. This is nothing but what is an intersection? Singleton 1, which is non-empty. Therefore, they are not separated. Right? So separated sets are always disjoint, but disjoint sets are not separated. Right? Second property about separated sets. See, if A and B are separated sets, no point of A is a limit point of B. That means derived set of A intersection B is an empty, and derived set of B intersection A is also empty. Why? Because once they are separated sets, A intersection B is an empty, and A intersection B closure is also empty. Therefore, already I told you that A closure contains derived set also, because A closure is nothing but what? A union its derived set. Therefore, derived set A intersection B, because A closure contains derived set, because it's just union of these two sets. So subset of empty set is always empty. Therefore, this is derived set is A intersection with B is empty. Similarly, derived set of B intersection with A also empty. Therefore, no point of A is a limit point of B, and vice versa. No point of B is a limit point of A. Right? These are two properties of separated sets. Right? Next is connected. Connected means you start with any subset of a metric space. is said to be connected. Already I told you geometrically it is a single piece. So by analytically it is not represented as a union of two non-empty separated sets. Two non-empty separated sets. It is not represented as a union of two non-empty separated sets. Right? So of course, this is nothing but what union means. It is a disjoint union because separated sets are always disjoint. Yes or no? Suppose you can take this example. R is equals to R with respect to discrete metric. Right? Suppose you can take R itself. You can take R itself. So R can be written as, this can be written as Q intersection with Q complement. Therefore, this, Q itself is a separated set. I can take A equals to B, B A equals to Q, B equals to Q complement. A closure intersection B is an empty, and A intersection B closure is also empty. Therefore, they are separated sets. Therefore, R is represented as a disjoint union of two non-empty separated sets. Right? R can be represented as a disjoint union of two non-empty separated sets. Therefore, it is not connected. Right? It is not connected. Suppose you can take any set, not only this set, with respect to same R with respect to discrete. Right? You can take any set whose cardinality is at least one. At least one. In fact, at least you can take at least two, not at least one, at least two, bigger than one. It is always disconnected with respect to discrete metric. Why? Because it can be represented as, the cardinality of A is bigger than one. As you know, that cardinality of A is bigger than one. Therefore, cardinality of A bigger than one means what? It contains minimum two elements. Without loss of generality, you can take X and Y, which are in E, which is not equals to, which is not, they are not equal, they are distinct. So therefore, E can be represented as, this E can be represented as X union E minus X. This can be treated as A, this can be treated as B. Therefore, these two are disjoint separated sets. Therefore, E is represented as two non-empty separated sets. E can be represented as union of two non-empty separated sets. Therefore, E is not connected, and it is disconnected. Right? Any set which is containing more than one element with respect to discrete metric is disconnected. Right? So what is more powerful? More powerful is any singleton is always connected. Any singleton. See, in compact, what is mean by any set is compact? When do you say that any set is compact? Finite set is always compact with respect to any metric. Similarly, any singleton is always connected with respect to any topology, any metric. Right? So we don't bother about singletons, just we bother about a set which are containing more than one element. Right? Any singleton with respect to any metric is always connected. Right? Suppose you can take another property. This is a fourth property. This is a property number third property. Right? Suppose you have R with respect to usual metric. What are the subsets of R with respect to usual metric are connected? Any subset of R with respect to usual metric is connected if and only if it must be an interval. It must be interval, or else E must be, or else E is singleton. Already we have seen that any singleton is connected. Right? What is meant by interval? Example, any subset of R which is connected if and only if it is an interval or singletons. Right? What is meant by interval? Suppose you start with R with respect to metric. Suppose you can take 1, 2, 3, 4 going on. Is it interval? No, because what is the definition of interval? Any points you take, any 2 points you take, right, in a set, the lying between, any point lying between them, should be a point of the given set. Right? Yet these 2 points are the elements of a set E. But if you take this point, midpoint, this is not a point of set E. Therefore, it's not an interval. Right? What is my interval? Any point lying between any two distinct points of a set lies in the set this property is satisfied by the E, then one can say that E is interval. Any point lying between any 2 points, distinct points of E should be in E. If E satisfies this property, then E is nothing but an interval. Question is, suppose you can take this 1 by 2 going on 1 by 3, 1 by 4. Is it connected? No, because it's not interval. Because you take these 2 points, this lying point, you can take, for example, point 61. Is it a point of this set? No. Therefore, it's not interval. Not interval means not connected. Means disconnected. Right? This is with respect to usual topology, usual metric only. Need not be true for another metric. Right? Suppose you can take set E equals to rationals. Is it connected? No, because it's not interval. Suppose you can take 2, 3 are rationals, but between there is a irrational is there. Therefore, it's not interval, not connected. Right? If you take E equals to irrationals, is it connected? Answer no, because not interval. Right? Suppose you can take E equals to open 1, 2. Is it connected? The answer is because it's an interval. It is always connected. Suppose you can take E equals to 1, infinity ray, right ray. Is it connected? Yes, because it's an interval and it's interconnected. Suppose it's left ray. Is it connected? Answer yes, because it's an interval. Is it clear? Suppose you can take E equals to 1, 2, union 3, 4. Is it connected? No, because it's not interval. No. Why? Because 1, 2, 3, 4. Suppose you can take a point here. You can take a point, for example, 1.9. You can take 3.1. But you take any point lying between them. For example, 2. Is 2 is a point of this one? No. 2 does not belongs to E. Therefore, it's not interval. Therefore, not connected. Is it clear? Hello? Is it clear?
Okay.
Okay. So that means that's our definition of a connected with respect to usual metric, right? With respect to usual metric. Next very important property is property number 1. Any two non-empty disjoint closed sets in a metric space are separated. These are very important property. This is a very, very important property in rooting. So any two non-empty closed disjoint closed sets, non-empty disjoint closed sets, if there are such a sets, there must be separated sets. Why? Because suppose you start with two non-empty and disjoint closed sets. What are A and B? They are non-empty disjoint closed sets. What I want to show is that A and B are separated. Therefore, I want to show that A closure intersection B is an empty. But A is a closed set. Once A is a closed set, A closure is A. Therefore, A intersection B. As you know that they are disjoint. Therefore, A intersection B closure is empty. Similarly, A intersection B closure. That is M is saying that B closure is nothing but what B, because actually B is a closed set. Therefore, this is in a B itself. Right? Why? Because B A closure is equals to A. Because A is a closed set. What do you mean by B closure? B closure is equals to B. Why? Because B is a closed set. Therefore, A closure intersection B is an empty, and A intersection B closure is an empty. Therefore, they are separated sets. Second one is any two non-empty, right? Disjoint open sets in a metric space are separated. Right? Suppose you can take A and B are two disjoint closed sets which are non-empty, which are closed sets. So which are open sets, You know, once they are open sets, the complement are always closed sets. You know, A intersection B is a, they are empty. A intersection B is an empty. Therefore, A must be contained in the B complement. Right? This complement of this, this is my X. You take like this. A should be contained in the complement of this. This is my complement. A should be contained in the complement. Right? So therefore, you know what is B? B is a closed set. B is an open set. So B complement is an open set. Sorry, B is a closed set. B complement is closed set. So closed set which is containing A, B complement is a closed set containing A. I already told you A closure is the smallest closure superset of A. Right? Therefore, A closure which is contained in B complement, because A closure is the smallest closure superset of A. This is after all B complement is after all a closed superset of A. You know that A closure is the smallest among all closed supersets of A. Therefore, A closure is contained in B complement, right? So take the intersection on B with B. So you know B intersection B complement is empty. So subset of empty is always empty. Similarly, one can show you that A intersection A intersection B closure also empty. Therefore, they are separated sets. So any two non-empty disjoint open sets are always separated sets. Right? Right. Third one is, suppose you have two balls which are disjoint. Suppose you have two balls. This is open ball centered P with radius R, and open ball. See, this is an outside of the ball. So outside of the ball means what? Distance between x comma p is bigger than R. So first one is open ball centered P with radius R inside. Second one is open ball centered P outside of the open ball. Outside of the open ball. You know, these are also separated sets. Yes or no? These are also separated sets, because you know what is this? These two are after all non-empty open sets. Understand? These two are non-empty open sets. Why? Because non-empty open sets, non-empty disjoint open sets. By a property 2, whenever you have a two non-empty open sets, non-empty disjoint open sets, therefore they're always separated. Right? So whenever you have two
sorry. Second point, sir.
Yeah. Second point is, whenever you have two non-empty disjoint open sets.
కిందికి ఇప్పుడు A is contained in B complement. A closure is contained in B complement అన్నారు.
Yeah, A closure is the smallest closure. A closure, you know that there is a property. A closure is the smallest closed superset of A. Smallest closed superset of A. Just B complement is after all a closed closed superset of A. B complement is after all a closed superset of A, but it's the smallest among all closed superset of A. It's smallest.
So therefore A closure superset కదా సార్, ఇది superset ఇది superset కదా అని.
సార్ సి మీకు ఇది ఆల్రెడీ మీకు ఇంతకుముందు ఎగ్జామ్ అంటే మీన్స్ కాన్సెప్ట్ చెప్పేటప్పుడు కూడా ఇదే డౌట్ అడిగారు. వేరే ఏ క్లోజర్ ఉన్నా ఏ క్లోజర్ కి సూపర్ సెట్ ఉందనుకోండి, సపోజ్ యూ టేక్ ఎనీ క్లోజర్ సూపర్ సెట్ ఆఫ్ ఏ, ఈజ్ ఎనీ క్లోజర్ సూపర్ సెట్ ఆఫ్ ఏ, రైట్? Suppose you can take B is a closed superset of A. B is a closed superset of A. Suppose you can take C is a closed superset of A. ఈ అన్నిట్లల్లో ఏ క్లోజర్ కూడా ఉంటుంది. ఏ క్లోజర్ ఆల్సో క్లోజ్డ్ సూపర్సెట్ ఆఫ్ ఏనే. ఈ అన్నిట్లలో చిన్నది ఏంటంటే ఏ క్లోజర్ అనమాట. ఈ అన్నిట్లలో ఈ నాలుగిట్లలో చిన్నది ఏంటంటే అన్నిటికంటే ఏ క్లోజర్. సో ఏ క్లోజర్ is contained in A and A closure is contained B. A closure is contained in C. These are always true అనమాట. So therefore B complement is after all a closed superset of A closed superset of A. But you know that A closure is among all the closed supersets is the least, is the smallest.
Okay sir.
Okay. Right, next is any connected set. Any connected set with containing two elements, with containing at least two elements, with at least two distinct elements. These are the routine problem. Distinct elements is uncountable. Right? Is an uncountable. Any connected set with containing at least two elements, always uncountable. Why? Because I can take this at least two elements, means you can take this x not equals to y, right? Right, these x and y are two distinct elements. You know there is a distance between them. We can call this distance as d. Right, this is denoted by d. You know d is positive because x and y are not equals, therefore d must be positive. Whenever d positive, we can choose a real number in between them by density property. We can choose a real number r, right? With a real number r, I can draw a ball centered x with radius r, right? Ball centered x with radius r, because I know r, I know d, therefore I know r. I can choose r in such a way that r is lying between 0 and d. So with respect to r, I can choose a ball centered. You know what is this? This is ball centered set of all y in y x such that this simply is nothing but ball centered x comma r. Means what? Distance between x comma this. This is my set, right? Second is outside of the ball. What is it? Outside of the ball, right? Outside of the ball. So this is my A set. You can take this as an A set. This is my B set. See, what is my A? Inside of the set. What is my B? Outside of the set. Right? So these two are non-empty separated sets. I already told you these two are non-empty. Why? Because this ball lo actually మీకు ఏమున్నదండి x ఉంది. x ఉంది కాబట్టి ఏంటి? x ఉంది కాబట్టి ఒక్క x ఉంది కాబట్టి ఏ non-empty. b లో ఏముంటదండి? b లో యాక్చువల్గా b అవుట్ సైడ్ కాబట్టి b లో y ఉంటది కదా. b లో y ఉందంటే b కూడా non-empty. What is A? A is inside, B is outside. Therefore, A intersection B is an empty. And A and B are what? Actually open sets because it's an open ball. This is outside of the open ball. Therefore, A and B are two open sets. So question is that, is it true actually? Is X is equals to A and B? Is it true? The answer no. What is my X? X is connected. Therefore, X cannot be equals to A and B because if X equals to A and B, X is can be represented as a union of two non-empty separated sets because any two non-empty disjoint open sets are always separated sets. You know, these two are separated sets, two non-empty separated sets because A and B are non-empty and A and intersection B is non-empty and they are open sets. Any two already look at the last property. Any two non-empty disjoint open sets are always separated sets. Once they are separated sets, therefore X cannot be written as a union of these two because why? Because X is connected. X is connected and union రాయలేం, right? So union రాయలేం అంటే therefore we can pick a point x in x such that x does not belongs to A and B. See, ఈ r వచ్చింది కాబట్టి r కి corresponding ఇంకో పాయింట్ వస్తుంది, right? This is with respect to r, right? So that means what? X is not in the union means what? X is not in A and x are in not in B. X is not in A means what? X should not be in inside. XR in should XR does not belongs to B means what? XR should not be outside. లోపల ఉండదు అవుట్ సైడ్ ఉండదు అంటే ఎక్కడ ఉంటుంది? బౌండరీ మీద ఉంటుంది కదా. ఎస్ ఆర్ నో? బౌండరీ మీద ఉంటుంది. దిస్ ఇస్ మై ఎక్స్, బౌండరీ మీద ఉంటుంది XR. అండ్ దిస్ ఇస్ మై R distance. So distance between x comma XR is R. Yes or no? So therefore what is this? This XR is always, when you give me R, ఇక్కడ చూడండి, just go back to this. When you give me R, I find an element when you give me an R lying between 0 to D. When you give me R is a point lying between 0 to D, we get a point which is in X, which is always subset of X, right? Because XR is a element of X. These are well subset of X. So once you give me R, I find an element in R. I find an element in X. So how many elements you get? Uncountable elements. Because once you give me R, we can find XR. Once you give me R, I can find another XR. Therefore, once you give me this, I can find uncountable elements. So left side set is uncountable set. So superset of uncountable is always uncountable. Therefore, X is uncountable. So this is very strong problem. It is in Rudin. Right? These are all problems in Rudin. Right? So any connected set with a distinct element, at least two distinct elements is always uncountable. Always uncountable. Right? Next property is using this property number 5, property number 6. So is any subset of a metric space is disconnected. These following three conditions are equivalent. Right? Is disconnected if and only if E can be represented as a disjoint union of two non-empty closets. Disjoint union of, because disjoint union of non-empty closets means what? They are separated sets. Separated sets unte disconnected aitadi kada. So disjoint union of two non-empty closets. Two non-empty closets. Right? So what is my third point? E can be represented as a disjoint union of two non-empty open sets. Next, second one, fourth one is, this is very important. There exists a non-empty proper close-open sets. What is mean by close-open? Both open and closed. Already told, both open and closed. So there exists at least one proper close-open sets Next. So if at least one of the condition is satisfied, one can say that A is disconnected. Example is, suppose you can take this R with respect to discrete, right? You know R is uncountable set. Once R is uncountable, we can pick an element. Once you pick an element, this is my singleton X. This is already I told you, any subset of R with respect to discrete is closed open set, means both open and closed in R with respect to discrete. So there exists, this is non-empty and not equals to R. Therefore, it is a proper non-empty closed open subset of R. Therefore, it is disconnected. Right? It is disconnected. Right? Or else R can be written as singleton X union R minus X. This is a closed set because you are in discrete. This is also closed set because it is discrete. So this is non-empty. This is also non-empty. This is closed. This is closed. Whose intersection is empty? Whose intersection is empty? Right? Because singleton X intersection with singleton X complement. Therefore, A intersection A complement is empty. Therefore, R can be represented as disjoint union of two non-empty closed sets. So by property 2, it is disconnected. Right? So this is very powerful tool. This is very, very powerful tool. Right? To prove, one can show that it is disconnected. Right? Next property number 7th. Suppose you have a metric space. Suppose my B set is connected. A is any subset of B, B is subset of A closure. Automatically, middle one is connected. So in particular, this is very, very important. This one is important. In particular, closure of a connected is connected. Closure of a connected is connected. Right? Suppose you can take see any R with respect to element. R with respect to element. Right? Suppose you can take this is my connected set. This is an interval, therefore it is connected. What is the closure? Close 0, 1. Is it connected? Yes, because it's an interval. Because it is an interval. So closure of the connected is always connected. Closure of the connected is always connected. Right? Closure of a connected is always connected. Right? Next is property number 8. Closure of a connected is connected. Property number 8. Any convex set in a nonlinear space. Any convex set. Convex. Any convex set in a nonlinear space is always connected. So when you go through the function analysis, what is meant by nonlinear space? It is connected. In fact, it is always connected. It is connected. So in particular, any ball, open ball or closed ball is always connected. And in particular, any convex set is in a nonlinear space is connected means what? Subspace is always a convex set because any finite linear combination is an element of this. So any subspace of a vector space, nonlinear space, is connected. Any subspace of a nonlinear space is connected. So these 3 properties are very, very important. Why? Because look at example. Suppose you can take this set of all symmetric matrices. Is it connected? The answer is because it's a subspace of 2 cross 2 matrices. So hence it is connected. Right? Suppose you can take a set of all 2 cross 2 matrices which are skew symmetric matrices. Is it connected? The answer is because it's a subspace. Therefore, it is connected. Suppose you can take set of all matrices, 2 cross 2 matrices, whose trace is 0. Is it connected? Yes, because it's a subspace. Trace of A plus B is equals to trace of A plus trace of B. Go back to your properties of trace. And trace of C into A is equals to C times of trace of A. Therefore, it's a subspace because right side are 0. Therefore, it's a subspace means what? Hence it is connected. So this is a very powerful tool, right? Any subspace of nonlinear space is connected. In fact, any convex set is connected, and any open set. See, open set in a nonlinear space is always a convex set. Any open set in a nonlinear space is connected. Convex. Convex is always connected, right? Next is next property. Property number.
Convex and convex set.
Yeah. Tell me.
Convex set.
Yeah, convex means looking like it's an interval, like looking like the property. Convex means any 2 points joining any 2 points, any line segment. In fact, see any subset of a nonlinear space or vector space, in fact, real vector space, is said to be convex. Any line segment joining any 2 points, of the set should be in E. If that happens, E is convex. Suppose you can take this. Is it convex? No, because I can take 2 points. Line joining them is outside. This piece is outside. Therefore, not convex. Is a triangle convex? Yes, because any 2 points join them, that should be inside. Is it convex? Yes, because any 2 points join them, should be line in the set. Therefore, it is convex. Is it clear? Hello? Is it
Okay.
convex? Yeah.
Okay,
So that
sir.
is a convex. So any convex is always connected. Subspace is always a convex because the subspace is nothing but what? I take any finite linear combination should be in here. Therefore, convex is nothing but only you are taking 2 elements. You are taking 2 elements. 1 minus t into alpha beta should be in E. This is analytical definition of convex. You take any 2 elements which are in E and take any point which should be in 0, 1. So this alpha beta are 2 points of the set E. So this is a line segment joining in alpha and beta. Alpha and beta 2 points of the set E. This is nothing but what is the equation of the line joining in alpha and beta, right? Therefore, it should be in E. This is analytical definition of a convex set, right? So therefore, automatically it is a subspace. Therefore, it is a convex, right? Next is
Open interval connected కాదన్నట్టు
open interval.
అదే పైన సెట్ లో ఓపెన్ ఇంటర్వెల్స్ ఇస్ నాట్ కనెక్టెడ్ అన్నది ఇక్కడనే ఓపెన్ ఇంటర్వెల్ కనెక్టెడ్ అని చెప్తారు.
Open interval connected in which metric space? Discrete లేదా వేరే మెట్రికా ఇంకే వేరే మెట్రికా?
పైన ఎక్స్ప్లెయిన్ చేశారు కదా.
ఓపెన్ ఇంటర్వల్ నేను ఎక్కడ డిస్కనెక్టెడ్ అని చెప్పలేదు, ఓన్లీ డిస్క్రీట్ లో చెప్పాను అనుకుంటాను. బట్ ఎక్కడైనా కనెక్టెడ్ అయినా రాసాను, ఎక్కడైనా కనెక్టెడ్ అని రాసాను. అన్ని కనెక్టెడ్ చూడండి, ఇవన్నీ చూడండి కనెక్టెడ్. ఇంటర్వల్ 1 to 1 minus infinity 1.
టూ ఓపెన్ ఇంటర్వెల్ యూనియన్ అనేది కనెక్టెడ్
Be connected. Union of connected sets may not be connected. Example, you start with R with respect to usual. Suppose this is my connected, yes or no? Because it's an interval. This is also connected because it's an interval. You take the union. Is it connected? No, because it's not interval. Not interval means not connected. Is it clear?
అట్ ద సేమ్ టైం హాఫ్ ఇంటర్వెల్స్ ఆల్సో నాట్ కనెక్టెడ్ అయితే.
Yeah, any interval is always connected, sir. Any interval in R with respect to usual. See, discrete లో తీసుకుంటే మళ్ళీ కాదు, ఎందుకంటే అందులో మోర్ దెన్ 1 ఎలిమెంట్ ఉంటుంది కదా.
ఓకే ఓకే సార్.
డిస్క్రీట్ లో తీసుకుంటే నేను చెప్పాను ఓన్లీ సింగిల్ టెన్సరే కనెక్ట్ అయ్యేది. హాఫ్ ఇంటర్వెల్స్ తీసుకోండి, ఆ రేస్ తీసుకోండి, ఇది కనెక్టెడ్ అయితే కాదు, ఎందుకంటే ఇలా మోర్ దెన్ 1 ఎలిమెంట్ ఉంటుంది డిస్కనెక్ట్. ఓకే, సో యూనియన్ ఆఫ్ కనెక్టెడ్ may not be connected, but suppose you take an additional condition. If each alpha is connected, means union of connected is connected provided they have a common point. Union of connected sets is connected provided they have a common point. Means intersection is non-empty. Suppose you can take this, right? You can take this. Suppose in R2, R2, you can take this. You can take this parabola y equals to minus x square. This is connected. It's a single piece. I'll tell you why this is connected later. It's a single piece. It is connected. I'll tell you this why it is connected. So it is connected. This also connected. Y equals to x square. And they have a common point 0. Therefore, it is connected. So E, what is E? E is equals to set of all right parabola and union of two parabolas. One is left side parabola, one is right side parabola. So is it connected? The answer yes, because this is connected, they have a common point. Therefore, union is connected. Is it clear? Is it clear? Hello?
Okay, sir. Okay.
Right, intersection. What about the intersection? Intersection of connected may not be connected. Connected sets may not be connected. Why? Suppose you can take A equals to suppose R square minus 0, 0. I'll tell you why it is connected. It is connected. In fact, it is pathwise connected. So it is connected. So any R square minus countable set is always connected. I'll tell you. So therefore, and that R cross singleton 0, this is also connected because it is pathwise connected. Therefore, it is connected. You take the intersection. What is intersection? This is what is my A? A is nothing but total plane except 0. What is my B? What is my B? My B is, what is my B? My B is total real line, total x-axis. So what is intersection? Anybody? What is intersection?
Empty.
No, x-axis. X-axis except
Oh, yes,
0.
yes, sir. Yes, sir.
Except 0.
Except 0, x-axis.
Yes or no? So that means set of all x comma 0 such that x is non-zero, x is a real number. Right? That means your set is like this. Sorry, your set is like looking like this. This one, this is not included. This one. Is the set, this set connected? Is this set connected? This is your set. This black shaded region. Is here connected? No. Why? Because it is looking at two pieces. One piece left side, second piece right side. So this is a closed set, yes or no? Because the left segment is always a closed set. This also closed set. So intersection of two, this can be written as, suppose you can take this E is equals to, this A intersection can be written as 1 union 2. Therefore 1 is closed, 2 is closed, they are non-empty, they are disjoint. Therefore A intersection can be written as union of two non-empty disjoint closed sets. Therefore A intersection B is disconnected. By definition, A intersection B can be written as union of two non-empty disjoint closed sets. Therefore A intersection B is disconnected. Is it clear? Yes. Next, see, look at this property. So before doing that user arguments, see, look at this property. So this is pathways connected. Actually, this is not in my syllabus, but it is very powerful. Path connected, pathways connected. You take any 2 points, in a topological space, they can be joined by a continuous path. So any line, any 2 points, if you take, they can be joined by a polygonal line. They can be joined by a polygonal line. Any 2 points, you give me this point, you give me this point, they can be joined by a polygonal line that is entirely in X, then that is pathways connected. Pathways connected means what? Any 2 points of X can be joined by a polygonal line. Can be joined by a polygonal line. Right? If that happens, that is connected. In fact, pathway is connected. So this is not in our syllabus, but this is a very powerful tool. Right? So any tool, see, suppose you take this example, R2. In R2 with respect to D2 usual metric, suppose x-axis. Suppose my set is x-axis. Is it connected? The answer is, because you give me 2 points, they can be joined by a line segment. should be entirely in the set. Therefore, it is connected. Is it connected? Y-axis connected? Yes, because any 2 points you give me, the line segment jointly simply these 2 points can be connected by a line segment that is entirely in the set. Any 2 points you give me this point, this can be joined by two line segment, polygonal line. Therefore, y-axis also connected, right? Suppose you can take r square minus 0. R square minus 0. Is it connected? Yes, because this is my r square. It's entire plane except 0. Entire plane except 0. Is it connected? Yes, because mere points and even I can join them by a polygonal line. Point I can join them by polygonal line. Therefore, it is connected. In fact, its pathway is connected. Is it clear? So any r square minus 0 is always path connected. In fact, any r power n minus a countable set is connected. Whenever n is bigger than 1. Whenever a is countable set. And this is also very, very important property. So r square minus 0, 0, same property, polygonal connected. This is nothing but polygonal connected. Therefore, r power n minus a, it should be connected. Right? Is it clear? Right?
Yes, sir. Yes.
Next property is, so 11th property, continuous image of connected is connected. Continuous image of connected is connected. That means you take this continuous function from x to y. Suppose E is my subset which is connected. E is a set which is connected. This set is connected. Look at the image in y. This is f of E. This is also connected under the continuous map. Right. So this is very, very powerful tool in metric space. For example, suppose you can take a circle in R2. Is it connected? Yes. By geometry, I already told you it is a single piece. Single piece is nothing but a connected. By geometry, look at the problem. It is by geometry, it is a connected. So by looking at the problem, we can say that we are in a position to say that it is connected because it's a single piece. But how to show it by analytically is that by applying the continuous image of connected is connected. So I can define a function, continuous function, look like this. F of t is equals to cos t sin t. Clearly it is a continuous map, right? Clearly it is a continuous map, right? Therefore, it is an interval. Interval is nothing but what? Already told you, connected, right? So domain is connected means what? This image also connected. But what is image? What is image? Total circle. S is connected. This is my S. This is connected. Is it clear? So continuous image of connected is connected. This is a very important example, right? Suppose you can take ellipse. X square by a square, y square by b square equals to 1. Is it connected? Yes, because the single piece is always connected. By looking at the example, we can say that. So by analytically, we can easily prove it by define a continuous map. F of t is equals to a cos t, b sin t. So simply its image is ellipse, your set S. It is connected. So continuous image of connected is connected, therefore it is S is connected. Right? Suppose you can take a hyperbola. Is it connected? The answer no. Right? Because it has two pieces, one piece left side, one piece right side. Therefore, it is not connected. By looking at the graph, we can easily say that it's disconnected. Right? Suppose you can take this. See, how can you prove analytically? It's the same strategy. So if you take any point in S, any point you take in S, this x should not be 0, right? Because if x is equals to 0, minus y square equals to 1, therefore y square equals to minus 1. Therefore, there is no real number whose square is minus 1, right? So x should not be 0. If x is 0, you are getting a conduction. So therefore, x should not be 0. So I can define a continuous map. F of x comma y is equals to, what is this? X is non-zero means what? I can define like this, x by mod x. What is x comma y is a point in S. You know, it is clearly continuous map because x is continuous, mod x is continuous, x by mod x is always continuous on S. On S, because S, when you take S element within S, the x should not be 0. It's a continuous map. What is the image? What is the image? Whenever x is positive, x by x 1. Whenever x is negative, x by minus x, this is minus 1. Suppose you assume that it is connected. Continuous image of connected is connected. Therefore, this must be connected. But is it connected? No, because it's not interval. Disconnected actually. Another way, this is disconnected. Why? Because it's not interval. So conduction, right? Therefore, it is not connected, right? Suppose you can take a rectangular hyperbola, right? Rectangular hyperbola, so like this, looking like this. You can take x positive, y positive. You can take like this. Suppose I can take x comma y is which is not 2, such that xy equals to 1. Is it connected? No, because there are two pieces. There are two pieces. This is my piece. This is my one piece. Therefore, it's disconnected by same strategy. I can define a continuous function like this. What is my continuous function? S goes to R. My continuous function is like this. So here x equals to y equals to x into y equals to 1 means what? Whenever x comma y belongs to 1 means x into y equals to 1. Therefore, x into y should not be 0. Therefore, either and x non-zero and y non-zero. Therefore, you can take my continuous function is like this. So by same argument, it is disconnected. Right? Next is fifth one. Suppose you have a problem like this. Suppose you can. So does there exist a continuous function? Does there exist a continuous function f from R to R such that f takes irrationals at rationals, f takes rationals at irrationals, f takes irrationals at rationals, f takes rationals at irrationals. So does there exist a continuous function? This is a very, very important problem. So is it true? Actually, no, because suppose you have a continuous function like this. Right? Already told you continuous image of connected is connected. You know that R is in interval. So connected. So f of R is always connected because it's continuous map. It is a connected subset of R because it's subset of R. Connected subset of R. What are the connected subsets of R? Already told you they are singletons. There may be singletons. They may be intervals. Are they singletons? No, because f takes rationals, f take irrationals at rationals, f takes rationals at irrational. Therefore, they are not singletons. They are not singletons. Therefore, f is non-constant function. Right? F FR must be interval. FR must be interval. Yes or no? FR must be interval. Any interval. So any interval of the form should be uncountable set. Right? One way it is uncountable. Second way, look at this. You know, this Q is countable. Image of countable is countable. Therefore, f of Q is countable. Because a Q is countable means image of countable. You know, here rational numbers also countable. This is countable. Therefore, subset of countable is countable. Therefore, f R minus Q is also countable. Countable union of countable is countable. This is countable. But what is this? F of Q union R minus Q. Therefore, what is this? F of R. You know, right side is countable means what? Left side also countable. So we are getting a conduction because in this case it is uncountable. In this case it is uncountable, but in this case you are getting countable. So conduction. Therefore, there is no such a map like this. There is no such a map. F takes irrationals at irrationals, F takes irrationals at rationals. There is no such a continuous map. This is very, very important question. Next is problem number 6. So does there exist a continuous function? Suppose suppose A is a connected, A is connected subset of R, right? Such that f takes Yeah. F-text rationals. What can you say? So yeah, how can construct the problem? So F-text. Yeah. Yeah, I can give you the example later because testing problem, but the thing is, yeah. Second is you can take this problem, this property. Suppose A and B are connected sets. If and only if a Cartesian product of connected is connected, right? If of course it is true for uncountable, any product, in fact, any product of connected is connected. Right? Example, in R2 with respect to Euclidean metric, R is connected, right? This is singleton 0 also. Singletons are always connected. So R cross 0 is connected. Right? It means x-axis is connected. Right? Is it clear? Right? So any product you can take. Suppose you can take singleton. This is connected. R is connected. This Cartesian product is connected. Means y-axis. Y-axis is connected. Right? So this is important. Right? Suppose using this application, suppose you can take like this set of all rational numbers such that set of all pairs x is a rational number and y is a rational number. Is it connected? The answer no. Not connected, because what is this actually? This is nothing but q cross q. So q is disconnected, therefore q cross q is disconnected. As you know that q is disconnected because it's not interval. Right? Suppose you can take this set of all order pairs such that x is irrational, y is irrational, y is not rational, means irrational. Is it connected? No. Because q is not connected. Of course, I can define, see, there are so many ways to show that it is disconnected. So here q is not connected. It is looking like that q cross r minus q. Disconnected. Right? Next, is it clear? So therefore Cartesian product is very, very important. Using this application, one can show this. Right? Next is property number, I don't know. Yeah. So next property is using this property, x is connected if and only if any continuous function, continuous map from x to 2 points at discrete space. 2 points at discrete space is a constant map. 2 points at discrete space. Any function from x to 2 points at is a constant function. Constant function. And non-constant functions undo x connected అయితే. Understand? X connected and then non-constant functions undo from x to discrete space. 2 points at discrete space. Right? Next is suppose you can take this general linear group. Is it connected? Is disconnected. Why? Already I told you, set of all a map, determined map is always disconnected. F of a equals to det a. Right? Suppose general linear group is connected. Suppose you assume that general linear group is connected. What happens? Continuous image of connected is connected. Therefore, f of general linear group is connected. But what is this? This is exactly precisely image of this such that a belongs to general linear group. But what is f of a? F of a is nothing but det of a, such that a is an element of general linear group. But whenever a is a element of general linear group, whose det is always non-zero. Whose det is always non-zero. That means what? This is nothing but non-zero numbers. We're going to get non-zero numbers. Right? Of course, it is an onto map. because you give me any number, I can assign a pre-image whose determinant is non-zero. So it's not to map. Therefore, this is r minus 0. You know, this is nothing but what? It's not interval. Not interval means not connected. Understand? So therefore, yes, your assumption is wrong. What your assumption? Your assumption is general group is connected. So you're going to get continuous image is connected. Therefore, you're getting a conduction. Therefore, this is disconnected. Right. Next is components. This is the last topic. Component means it's a maximal connected subset. Maximal connected subset of a metric space. Means it should be it's looking like maximal ideal. You know, maximal ideal. There is no proper ideal which is containing that. Similarly, maximal connected set. Maximal connected set. So give an example. Suppose you can take this R with respect to this. What is the component of this? R itself, because it's a maximal connected set. It's a maximal connected set, hence it is component. Understand? So see, why don't you take this? Why don't you take this? This is also connected, okay, but it's not maximal because it's contained in another connected set. It is contained in another connected set. Therefore, it is not component. Understand? R is a maximal connected set, hence it is component. Suppose you can take discrete R with respect to this discrete. What are the components? What are the components? Only singletons. Only singletons are component, because any set which is containing more than one element is disconnected now. So that must be connected and that must be maximal. Connected kavali, maximal kavali. Connected discrete space lo em untayi? Singletons. Kada? So every singleton is component. Only singletons are components. Right? So these are components. Right? Suppose you can take this Q with respect to usual metric. What are the components? Only singletons. This Q is not connected. Yes or no? So any set which is containing more than one element is disconnected. Therefore, this is actually not connected. Yes or no? Disconnected, not connected. Why? Why? You know, Q can be, of course, Q is not interval, or else Q can be represented as Q in intersection with minus root 2. Root 2. Of course, we can take like this. Q can be written as some open set like this, union Q intersection with the rationals which are right side to root 2. You know, this is open in Q. Yes or no? Because it's an open in R. Therefore, intersection with Q means what? It's an open in Q. This open in R, intersection with Q means what? It's open in Q. Therefore, Q can be written as disjoint in num, because they are disjoint. These are irrationals. These are rationals left side to this. These are rationals right side to this. They are disjoint open sets in Q. Therefore, Q can be written as a disjoint in to non-empty open set. Therefore, Q is disconnected. So what are components? Only singletons. We can show it actually. Any set which is containing more than one element is disconnected. So that is an exercise. You need to show it. So singletons are components. So it's enough to show that any set which is containing more than one element is disconnected. Any subset of Q which is containing more than one element is disconnected. It's an exercise. Do it. Same strategy. So only singletons are components. Is it clear? So with this, I can conclude connected space. Right? With this, I conclude connected space. So metric space is over. Right? By tomorrow, I'm going to complete topology in one class. Yeah. Any doubt? Hello.
Sir, thank you, sir. Tomorrow we have a CSR exam, sir.
Okay.
So give some tips and advices to those who are appear from CSR examinations. So Anish sir kuda unnaru. Anish sir, are you there? Sir.
Yes, sir.
Sir, మీరు మాట్లాడండి సార్. ఎట్లా అటెంప్ట్ చేయాలి ఏంటి అనేది. రేపు CSR ఎగ్జామ్ ఉంది సార్.
Okay, 18th.
రేపు ఆఫ్టర్నూన్ 16. ట్రిప్స్ ఏమైనా చెప్తారేమో.
అండ్ సిఎస్ఐ గెస్ అంటే క్వశ్చన్ పేపర్ రియల్ అనాలిసిస్ అండ్ అల్జిబ్రా, లీనియర్ అల్జిబ్రా బాగా చదవండి. స్కోరింగ్ టాపిక్స్ కాబట్టి రియల్ అనాలిసిస్ అండ్ లీనియర్ అల్జిబ్రా అండ్ కాంప్లెక్స్ అనాలిసిస్ ఈ 3 చదివితే సిఎస్ఆర్ వస్తుంది. ఈ 3 ఎందుకంటే స్కోరింగ్ ఇప్పుడు కాంప్లెక్స్ అనాలిసిస్ లో కూడా 30 to 40 మార్క్స్ వస్తున్నాయి, 35 to 40. మళ్ళీ ఈజీగా ఉంటుంది కోర్స్, చాలా ఈజీగా ఉంటుంది కాంప్లెక్స్ అనాలిసిస్ కంపేర్ టు రియల్ అనాలిసిస్.
పార్ట్ సి మీద ఎట్లా కాన్సంట్రేట్ చేయాలి సార్? పార్ట్ సి లో ఎక్కువ స్కోర్ ఉంటుంది
అంటే మెయిన్ ఏంటంటే సార్ ఎక్కువ ప్రాబ్లమ్స్ చేయాలి. ఇప్పుడు మనం ఏం చెప్తున్నాం సార్ ఇక్కడ? యాక్చువల్గా థీరం ప్రూఫ్ చెప్తున్నామా? కానీ యాక్చువల్గా దాంట్లో చాలా నాలెడ్జ్ ఉంటుంది. యాక్చువల్గా అప్రోచ్ అసలు యాక్చువల్గా అబ్స్ట్రాక్ట్ అంతా అందులో ఉంటుంది. సో ఆ థింకింగ్ లెవెల్స్ అన్నీ పోతాయి. కాబట్టి వాళ్ళు చేయాల్సిన పని ఏంటంటే ఈ మనం క్లాస్ అయిపోగానే వాళ్ళు యాక్చువల్గా ప్రాబ్లమ్స్ ప్రిపేర్ అవ్వకుంటూ థీరం ప్రూఫ్ చేయాలి. యాక్చువల్గా థీరం ప్రూఫ్ చేసుకుంటూ ప్రాబ్లమ్స్ చేస్తే, ఎక్కువ ప్రాబ్లమ్స్ సాల్వ్ చేస్తే ఎక్కువ ఐడియాస్ వస్తాయి, అటాకింగ్ స్కిల్స్ పెరుగుతాయి.
మీరేమన్నా ట్రిక్స్ ఏమన్నా వాళ్ళకి ఏమన్నా అడ్వైస్ చేయగలరా?
ఓకే సార్, అంటే అటెంప్ట్ అయితే ఇప్పుడు